Okay, so good afternoon, everyone. Good afternoon, dear panels. Good
Hello.
afternoon. Good afternoon also to my advisor. The title of my study is shown on the screen, and this is a um, sample video of the actual shelling operation.
Excuse me, Mr. Weber.
Yes, sir.
Did you copy the email? Did you copy it? Try again, please. Try again.
Okay, sir. Wait, sir. Hmm. I, I actually have another. I have no headphones, so is my audio clear now, sir, or not?
Yeah, Mr. Weber, you may turn off your video first para mas malakas yung
Okay.
audio.
What about ma'am now? Okay na po ba, ma'am?
Yes, okay naman.
Okay. So let me continue my presentation. Let's recall what was the research topic or the technical issues. So there are different dehusking equipment such as steel huller, rubber rollers, and run disc sheller. My study was focused or centered on a development or small development on underrun disc sheller. Even though these technologies were originally designed and used for removing husks in small grains, there are actually no reason not to extend or adopt these technologies in other food crops and determine their effects. For underrun disc sheller, it has two basic parts, the horizontal disc, the upper part, and the lower part. The upper part is fixed, and the lower disc part is the one that is rotating. The two discs are covered with abrasives. This technology is very simple in operation. It has low running cost, and the abrasives are very inexpensive and can be made or remade on site. Those are the advantages of this technology. But the main disadvantage of this technology is that it produces a high grain leakage and that it causes also an abrasion to the outer bran layer of the grain. So the basic mechanism of this technology is that after the grains are fed onto the top, it starts to move radially outward because of centrifugal pressure that is developed between the two discs, and the work of friction that is created between the interfaces of the grains and the abrasives cause the removal of the outer part, which is the husk. But again, the main disadvantage is that it causes too much grain leakage and abrasion to the outer bran layer of the grain. So the proposed solution or the perceived solution is to allow the upper part of the disc to rotate as well. And in doing so, you can regulate or down-regulate the amount of work of friction that is developed between the interfaces while maintaining enough centrifugal pressure or centrifugal force to keep the food crops in moving radially outward. So it was the general objective of this study to develop a small-scale underrun disc sheller with variable flip speed and replaceable disc type for peanut variety. The specifics were: 1. Develop an underrun disc shelling technology that minimizes seed breakage percentage by providing a variable disc speed that regulates centrifugal effect. Second objective is to fabricate the system with the following components: top and bottom rubber disc housing, two induction motors, control unit, collection box, and a pedestal. Third is to test and improve the project prototype by determining the effect of the clearance, the slip speed, and peanut variety on the performance indices of the sheller. And the last is to evaluate the acceptability and or performance of the project prototype. The methodology began by purchasing a 3.5-month-old Padpad variety from Libertad Marketplace in Bacolod. The ground nuts were cleaned, any defective or damaged pads were removed, and they were then solar dried for 2 to 3 days. The initial moisture content was measured by a standard AOAC official method using binder ED series drying chamber. And during the experiment, the two variables that were manipulated are the lower disk speed and the clearance, each of which has two levels. For clearance, there are 3.0 cm and 2.8 cm. For lower disk speed, there are 30 Hz and 35 Hz that are produced by the VFD, the variable frequency drive, or there are 15 RPM and 9.67 RPM in the lower disk rotation. And the data were analyzed using Unita 2018 by a 2x2 full factorial design. This is an sample video again of the actual testing, and the data collected is shown on the screen, and they are arranged in standard order tables where we have a clearance and VFD. We have 2.8, 30, 2.8, 35, 3, 30, and 3, 35. And the data gathered were total mass, unbroken kernel mass, and the broken kernel mass. Let's go now to research findings or results. A summary of descriptive statistics is shown in Table 5. We have the feed, the unbroken kernel, the broken kernel at 3.0 and 2.8 clearance, and lower disk speed of 15 RPM and 9.67 RPM. And we can observe it quickly that the best result can be achieved using clearance of 3.0 cm, and it doesn't matter much whether you use low speed or high speed. Table 6 is a summary of full factorial design. We have two factors, each of which has two levels for a total of 4 different experiments. Each experiment has 3 replicates for a total of 12 experiments or 12 runs. All terms are free from aliasing. It just means that the design is full factorial design. There are no confounding terms. Oops. Analysis of variance was also included in the data analysis, and results showed that analysis of variance for DE, decortication efficiency, and PKD, percent kernel damage, are identical because DE and PKD sums up to 1 or 100%. And data showed that only clearance is highly significant among two variables at alpha of 0.01. Another way to present the data is by using Pareto charts. In this figure, we can see that factor A in both DE, decortication efficiency, and PKD, percent kernel damage, is the only factor that is significant because it is located on the right side of the vertical dashed line. The gray bar indicates positive effect. The black bar indicates negative or decreasing effect. So clearance, the effect of that on decortication efficiency is that it increases the efficiency, while the same factor has a negative effect or decreasing effect on the percent kernel damage, and that is good. That is good. We have to increase DE and we have to reduce the damage. For response surface, contour plot of DE and PKD, we have y-axis the lower disk speed and the x-axis as the clearance. It can be shown here that if you are going to operate at 3.0 cm clearance, the choice of lower disk speed is very trivial, because you can see here the dark green area, that's where the cortification efficiency is greater than 98% at 3.0 cm clearance. The same is true with percent kernel damage. If you're going to operate at 3.0 cm clearance, it doesn't matter if you use low speed or high speed, your percent kernel damage is less than 2%. But it can also be shown here that there is a interaction effect between the low speed, between the disk speed and the clearance, because the contour is curved. It has a curvature. So this is now the summary of the results. Different studies from different researchers are included for comparison. Their statistics are represented in bold numbers, while the result of my study is represented in normal case, and they are placed alongside. As all researchers used ground nut except Uluwuli. That's why we have NA for Uluwuli. And the reason I include Uluwuli is because for reference purposes of the indices that were used, which is the percentage effective cracking and the percentage of breakage. So all researchers used ground nut, Uluwuli used Shina. So they are not valid for comparison. That's why the results is NA for Uluwuli. But I have the results there using the statistics or formula by Uluwuli. MT is the total mass of ground nut or feed. MUK is the mass of unbroken kernels. MBK is the mass of broken kernels. And MUNS is the mass of unshelled seeds, all after operation. So let's go first under the column of GORE. We have damage percentage, we have unshelled seeds percentage, and we have the shelling efficiency. As you can see, the unshelled seeds percentage of my results is 0 because there were no groundnuts that were put in the hopper that came out unshelled. All groundnuts were shelled, not a single one that is unshelled. So using that statistic, the results showed that the unshelled seeds percentage is 0%. So consequently, the shelling efficiency is also 100% because these two sums up to 1 or 100%. And if you compare that to the result of GORE, the difference is not that quite, or it's not really significant. 100 compared to 98.9 and 0 compared to 1.2. With respect to damage percentage, the formula is MBK over MT. That's the mass of the broken kernels over the mass of the total, which includes the broken, unbroken, and the mass of the shells. And again, the results showed that at 3.0 cm, does it matter if LS or HS, the damage percentage is less than that of GORE. Again, there is not much difference in the statistics. Let's go now under YITAO. First, we have the shelling percentage. The shelling percentage formula is MUK plus MBK over MT. And as you can observe, the shelling percentage is low, 87.0 for YITAO, and mine played around 67, 70, 74, 67. And there are reasons for that. The reason is in the denominator, because MT is the mass of the unbroken kernels. The mass of the broken kernels and the mass of the shells. So this statistic or this index or this formula cannot be used for cross-variety comparison, because what it really does tell us is the percent of the kernel and not if the efficiency of the shelling, because it will not approach 100% because there will always be mass of the shell in the denominator, because the total limit of your numerator, the MUK and the MBK, that is the mass of the kernel. So the limit of this equation equals that of the percent mass of the kernel. That's why the statistics are low, because it does not approach 100, but it does approach the percent of the kernel. And sampling, I do a sampling of the PAD and the percent of the kernel compared to the total weight is around 74 plus minus 1.26, 72 plus minus 1.26. So again, if you translate this one to other statistics, it will be very close to that of Mishra. So let's go now to the last two columns. The last two columns are the only true indices that can be measured for valid comparison across variety, because the denominator does not include the mass of the shell. We have the 4% kernel damage, we have MBK, mass of the broken, divided by the mass of the kernel. For the cortication efficiency, we have the numerator, MUK, the mass of the unbroken kernel, over the mass of the kernel. So the result is quite accurate, because it does not include the confounding effect of the mass of the shell, because different variety has different shell percentage. Some are thick, some have thicker shells, some have thinner shells. And as a result, again, for a 3.0 cm clearance, it doesn't matter if low LS or HS, the percent kernel damage of my study shows 1.5 and 1.7, below that of 4.0 by Yitao. And for the cortication efficiency, we have 98, around 98% at 3.0 cm clearance, quite better than that of Mishra, which is 74.4. So that is the explanation of this summary. So in conclusions, clearance is the single biggest factor that contributes to an increase in the cortication efficiency and a reduction in percent kernel damage. At 3 cm clearance and high-speed lower disk speed, 98% DE and 1.5% PKD were achieved. Effect of lower disk speed within the range that was operated is insignificant. Next. Performance indices with total mass empty as denominator are not reliable for cross-variety comparison, because each variety has distinct seed parts percentage. These are percent effective cracking, percentage of breakage, damage percentage, and shelling percentage. So they are not really valid for cross-variety comparison. Unshelled seeds percentage and shelling efficiency by Gore can be used to gauge the performance of shelling operation, since it refers only to what proportion of seeds were shelled or still unshelled relative to the feed after an operation. So unshelled seeds percentage and shelling efficiency can be used to gauge the shelling efficiency of different technologies. Next, only percent kernel damage and decortication efficiency are valid for cross-variety comparison, because it investigates the quality of the shelled kernels. So while unshelled seeds percentage and shelling efficiency is used to gauge between shelling technology of different shelling efficiency of different shelling technologies, percent kernel damage and decortication efficiency can be used to gauge the quality of the shelled kernels. And the last conclusion is flexible rubber grooved discs are excellent for shelling, because it mimics the delicate and soft hand peeling action. So that would be all. Thank you for your attention.